What's going on, everybody? So let's talk about position, velocity, and acceleration in terms of functions and their derivatives. All right. And so position, velocity, and acceleration are going to be things that are terms that you're going to see a lot in calculus, physics, dynamics, whatever else you're going to take. Okay. And so you're going to know that these are all going to be one or two derivatives away from each other. And so in terms of functions, the derivative of position is velocity, and the derivative of velocity is acceleration. A more intuitive way you can think of this is velocity is the change in position over time, because that's what a derivative is, right? And acceleration is the change in velocity over time. And so if you have a position function that looks like this, let's say S of t, t stands for time. And so let's say you have S of t is equal to, let's say, t squared plus 3t plus 5, all right? So in terms of positions, and this is probably negligible, but the units are probably meters or something like that, right? If you want to get from position down to velocity, which is presented by v of t, a sense or a function of time, it's going to be the derivative, in this case with respect to t, right, of your position of this function right above here. And so to do that, it's going to be the derivative of the first term plus the derivative of the second term plus the derivative of the third, okay? And when you do that, you get the derivative of t squared, which is 2t, plus the derivative of 3t, which is 1 times 3. And then t, when you subtract 1 from the exponent, it's 0, and t to the 0, which is 1, right? And so you get 3 here, plus the derivative of 5. 5 is a constant, and the derivative of a constant is always 0, right? Plus 0, and so you end up getting 2t plus 3, and this is your velocity function. If you want to get your acceleration now, right, all you have to do is take the derivative of your velocity function. And so your acceleration at this point looks like this. A of t, right, a function of time, is the derivative with respect to t of velocity. And so it's just the derivative of this first term plus the derivative of this second term. And so when you do that, derivative of 2t is just 2, right? Because 2t to the 1, technically, so 1 times 2 is 2. T to the 1 minus 1, right? Subtract 1 from your exponent, it's 0. And t raised to the 0 is 1, so you get this. Plus the derivative of 3, which is a constant, is 0, right? And so you get your acceleration. In terms of units, velocity is meters per second in this case, and acceleration would be meters per second squared, right? For those of you who know about gravity, you know. And so this is the concept, right? Just taking one derivative to go from here, position, to velocity, and taking another derivative to go from velocity to acceleration, okay? So let's see how this stuff works in terms of problems. So let's look at number 1. It says based on the position function, right? You're given this first one, and you want to keep track or know what information am I being given? Am I being given position or velocity, right? Because if you're being asked to calculate acceleration, right? If you're given position, you need to take 2 derivatives, right? The first one to get to velocity, the second one to get to acceleration. If you're given velocity and are asked to find acceleration, you only need to take 1. So you need to be careful, okay? And so this is position, and you're asked to calculate the velocity at t is equal to 0 seconds. You're asked for an actual value, right, at a given time point. So this means you're going to get a numerical answer or value, okay, not a function. And so let's get from position to velocity first. So we said that the velocity with respect to t is going to be the derivative with respect to t of the position, and that's going to be the derivative of the first term plus the derivative of the second term. So derivative of 3 sine t, right, t over dt of 3 sine t. I know I was going a bit faster up there, plus the derivative with respect to t of t squared, right? That's going to be, and here's a little trick, when you have a coefficient, sorry, a number out in front, right, of your variable, you can always move it out front, right, of the dt, and you can just get 3 times the derivative with respect to t of sine t plus, and then this stays the same. Okay, so there's a little trick for you. And so this becomes 3 cosine t, because derivative of sine is cosine, okay, plus 2t, right? And so now that we have our general velocity function, right, now all we have to do is plug in t is equal to 0. So now we have velocity evaluated at 0 is equal to 3 times cosine of 0 plus 2 times 0, okay? And so when you do that, you're going to get cosine of 0 is going to be 1, so 3 times 1 plus 0, so your velocity at t is equal to 0 is equal to 3 meters per second, okay? And that's what you got here, all right? And so let's go from here, and we're going to move into acceleration, okay? And when we're getting into this, I do want to point out there is a difference between instantaneous acceleration and average acceleration, okay? The big difference is average acceleration takes into account the time interval that you're calculating over. So notice that when you're calculating instantaneous acceleration, it's kind of like when you get a speeding ticket, okay? You're trying to get your acceleration at a single snapshot at t is equal to 10 seconds in this case, okay? When you're asked to calculate the average acceleration, right, you're asked to average it essentially over the interval from 2 seconds to 5 seconds. And so let's get into it, and then you'll see what I'm talking about, hopefully. So this is our position function, and we said that in order to get from position to acceleration, we need to take 2 derivatives. So 1, 2, okay? So let's get our velocity function first. So velocity is the derivative of our position function, okay? And that's going to be the derivative of the first term, 2t cubed, plus the derivative of the second term, right, minus the derivative of the third term. Careful of your signs, right? And so we fill this out. 3 times 2 is going to be 6. T stays there. Subtract 1 from 3, you get squared. So our first one, we're done. Plus 2 times 3, again, it's 6. T stays there. 2 minus 1 is 1, right? There's a 1 here. I'm going to leave it how it is. Minus the derivative of 7. 7 is a constant, right? Derivative of a constant is always 0, right? So this is it right here. This is our general velocity. Now to get to acceleration, we need to take one more derivative because acceleration is the derivative, right, with respect to t of, I'm going to write velocity, or v of t, okay, this right here. And so that's going to be the derivative of this term plus the derivative of this term. So the derivative of the first one is 2 times 6 is 12. T stays there. 2 minus 1 is 1. But this is 1. I'm going to leave it. Plus, this is technically 6t to the 1. 1 times 6 is 6. Right? T. When you subtract 1, 1 minus 1 is 0. Anything raised to the 0 is 1. So I'm going to go ahead and get rid of that t. Okay? So 12t plus 6 ends up being our acceleration, our general function. Right? This is it right here. And now for our instantaneous acceleration at a single point. All we got to do is plug in t is equal to 10. Okay? So acceleration at t is equal to 10 is equal to 12 times 10 plus 6. So 120 plus 6 is 126. So there goes our acceleration. And this should be meters per second squared, not that the units are going to make a big difference for us right now. Okay? So this is instantaneous acceleration, and again, this does not include averaging over time. Now we're going to look into average acceleration, which does take into account the interval. Okay? And so same thing here. Since it's based on 2b is based on the same position function, we have already calculated our acceleration general function, right? Our acceleration was 12t plus 6. That's what we found right here, and I'll box that again. And so in order to calculate average acceleration, actually, we're not going to use our acceleration function. Why, you might ask? It's because how we defined acceleration at the beginning. Acceleration, in terms of average acceleration, right, when you're considering the time interval, is the change in velocity divided by the change in time. And so in this case, we're not going to use this. We're actually going to use our velocity function, which is going to be 6t squared plus 6t. That's what we found right here, okay? So this is what we are using, right? Little hat trick. And so the average acceleration, A for acceleration, AVG for average, think of this simply as the change in, the delta, the change in velocity divided by the change in time, okay? So this could be a shorthand way of memorizing it while you're learning. And so in this case, we're considering the time from 2 seconds to 5 seconds. And so the change in velocity is going to be the velocity evaluated at our later time point, 5 seconds, minus our velocity evaluated at our first point, 2 seconds, divided by the change in time. So 5 seconds, right, the later time, minus 2 seconds. Now, all we have to do is plug in 5 and 2 into our function in order to get these values, and we can solve. So velocity at 5, so this is going to be, what is it? Let's write this out, actually. 6 times 5 squared is 25, plus 6 times 5 is 30, okay, minus velocity at 2 seconds is going to be 6 times 4 plus 12. All this is going to be divided by 3, all right? And so when you chuck that into a calculator, you're going to get 180 minus 36 divided by 3, which is going to end up giving you 48. Okay? So 48 is going to end up being your average acceleration, and just for means of completion, acceleration is generally meters per second squared. Just make sure of that. But this is the takeaway from today, right? Is to know that to get between position, velocity, and acceleration, like you see here, all it is through derivatives. So one derivative to get here, one derivative to get there, okay? And so I hope this made sense, and if you got it, then really good job. If not, it's totally fine. Take your time and try to learn it, yeah? But if you have any questions, concerns, please leave them below, and I'll get back to you as soon as I can, okay? Have a good day, everyone.